Hello, we have learned about geodesics in hyperbolic plane or Euclidean plane. In general, geodesics are length minimizing paths. In hyperbolic plane or Euclidean plane, so the geodesics are simple. So in a hyperbolic plane, we have seen that. So if you take the upper half plane model of the hyperbolic plane, so geodesics are vertical lines and semicircles whose centers lie on the real axis. In Euclidean plane, the geodesics are the straight lines. Now, if you take a surface with some metric, so the geodesics means the length minimizing paths, so that will be very complicated. For example, if we take sphere, so one can prove that an arc of the great circle, so that will be a geodesic. In sphere, you can get 2 points. In fact, you can take 2 antipodal points. And so you can get 2 arcs of a great circle, which are geodesics. So therefore, so this sphere, so that is not a unique geodesic space. So hyperbolic plane, Euclidean plane, so they are unique geodesic space, but unit sphere, so that is not a unique geodesic space. So in sphere, still the life is very simple. So the geodesics are also very simple kind of nature. But if you take torus or a surface closed orient, let us take closed orientable surface of genus greater than equals to 2. So it admits a hyperbolic metric. So with respect to those metrics, so the geodesics in this surface, torus or hyperbolic surface, so they'll be very complicated. So we'll look into some of these things. Okay, so let us take a surface. So let S be a surface with some metric. And by geodesics, we mean length minimizing paths. So let us first take the surface to be sphere. S2 is the unit sphere in R3. In spherical coordinates, you can write the metric, the Riemannian metric as follows. So dA square, that is the square of the line element. So that is equal to d theta square plus sine square theta d phi square. Okay. Now let us take 2 points on the unit sphere and try to find out the length minimizing path between those 2 points. This is my sphere. First, let us take 2 points in this meridian circle. So what is this meridian circle? So this axis, this vertical axis is Z, and suppose this axis is X, and this axis is Y. So this is my unit square S2. So intersection of S2 with this XY plane. So that will be my meridian circle. So let us take 2 points here on this circle, meridian circle. Let it be P and Q. So in terms of spherical coordinates, you can write P as theta 1 comma 0 and Q as theta 2 comma 0. And so where this theta 1 and theta 2 lies? So theta 1 and theta 2, they lie in the interval 0 to pi. So 0 less than theta 1 less than pi, and 0 less than theta 2 less than pi. And also let us take theta 1 to be less than theta 2. Okay. So now observe that. So there are two arcs of this great circle connecting P and Q. So one is this thing. So this is my alpha 1. And the other one, it is the other part of the great circle. It is alpha 2. Now observe that length of alpha 1 with respect to the metric is nothing but equal to theta 2 minus theta 1. So that you can compute from this formula, d square equals to d theta square plus sine square theta d phi square. So in order to compute length of alpha 1, d of phi is 0 because phi is constant. Therefore, length of alpha 1, so this will be equal to integration theta 1 to theta 2 d theta. So that is equal to theta 2 minus theta 1. And length of alpha 2, so this will be equal to 2 pi minus theta 2 minus theta 1. And observe that because we have taken this theta 1 and theta 2 in the interval 0 to pi, and theta 1 is less than theta 2. So theta 2 minus theta 1 will be less than 2 pi minus theta 2 minus theta 1. So this will imply length of alpha 1 is less than length of alpha 2. Okay. So this is about only these two paths, alpha 1 and alpha 2. And now let us take any other path, beta, joining this P and Q in S2. So let beta be any, let us take differentiable path, or you can take piecewise differentiable also. In S2, joining P and Q. So in terms of spherical coordinates, beta t, let it be equal to theta t comma phi t. T is varying in some interval. So length of beta, So this will be equal to, suppose t is varying in this interval t1 t2 such that theta of t1 is equal to theta 1, theta of t2 is equal to theta 2. Length of beta, it will be equal to this integration t1 to t2 root over d theta dt whole square plus sine square theta t times d phi dt whole square dt. Now this one is always greater than equals to integration t1 to t2 root over d phi dt whole square dt, and which is nothing but equal to integration theta 1 to theta 2. Sorry, I made one mistake here. So this is not d phi dt, so this is d theta dt whole square dt. This integration is equal to theta 1, theta 2, d theta, that is equal to theta 2 minus theta 1, and that is equal to length of alpha 1. So this implies that alpha 1 is a length minimizing path. So alpha 1 is a geodesic from P to Q. Now observe that, so if I have taken this theta 1 to be equal to 0, theta 2 equal to pi. So let me draw this picture. Suppose this is my point P and this is my point Q. Now there are two choices. So alpha 1, and let us call this to be my alpha 2. So we have two choices. So we can check that. So then length of alpha 1 is equal to length of alpha 2. So there are two geodesics connecting P and Q. So for P, this theta 1 is equal to 0 and Q theta 2 is equal to pi. So you have two geodesics connecting P and Q. So therefore this pair, it is not a unique geodesic space. Okay. So we have taken this PQ points in the meridian circle of the sphere. Now if I take any other 2 points, we take other 2 points P prime and Q prime in the sphere S2. We know, so there exists an orthogonal transformation which will take this P prime to a point P on the meridian circle and Q prime to a point Q on the meridian circle. Okay, so let me write down what I've said. So let P prime Q prime belongs to S2. So there exists a, an orthogonal matrix A belongs to O2 such that A of P prime is equal to P and P lie on the meridian circle. Let me write down like this. And A of Q prime is equal to Q, which also lies in the meridian circle. And this action is by isometry. So the orthogonal transformation, it acts on S2 by isometry. So A is an isometry of this S2. So therefore, the distance between P prime and Q prime will be same as the distance between P and Q. And now we know that there exists a great circle passing through this P prime and Q prime. So draw a great circle passing through P prime and Q prime. So this orthogonal transformation A, it will take the blue great circle to the black gray circle, this meridian circle. So therefore, here, so this portion of this great circle, this arc of this great circle joining P and Q prime, so that will be a geodesic. So let alpha be an arc of great circle joining P prime and Q prime. And also we assume that, so this angle between this OP prime and OQ prime, so that is less than pi. So this is less than pi. So then so this alpha will be a geodesic. So here we have assumed that this angle P prime O Q prime, so this is less than pi. So this we have assumed. So this alpha, it will be a geodesic. So the geodesics in this pair, so they are part of a great circle. So now let us move to torus. So here I'll take torus with Euclidean metric. So that is this flat torus. Let me draw a picture of the flat torus that is obtained by identifying the opposite sides of a square. This side is identified with this side and this blue vertical side is identified with the other blue vertical side. So I'll get a flat torus. So now let us take 2 points in this torus. Let us take 2 points P and Q. So now our goal is to find a length minimizing path joining P and Q. So one can think that you just join this P and Q by a straight line. So if I just join it by a straight line, let us call it to be alpha. So this alpha, the straight line alpha, in the torus, flat torus, may not be length minimizing path joining P and Q. So this alpha, it may not be geodesic. Why? So I can get hold of another path joining this P and Q in this way. So let us take this horizontal line segment, this green one. So this green horizontal line segment will hit the left edge, call it to be P prime. P prime, again, it is identified with this point P double prime, and go up to a point Q double prime, which is at the same level at Q. Join this Q and Q double prime by a horizontal line segment. So let us take beta to be P, this lines horizontal line segment PP prime. P prime, again, it is identified with P double prime. So take the vertical line segment P double prime Q double prime, and then take Q prime Q double prime Q, this line segment, horizontal line segment. So this beta, it is again is a path between P, P and Q. So it may happen that, so this length of beta, it is less than alpha. So therefore, so geodesics in this torus, it will be little complicated. But if we want to find close geodesics, then that will be simple. By a closed geodesic, what do we mean? So first of all, so this closed geodesic, it is a simple closed curve. So again, so what is a simple closed curve? So it is a map. So alpha is said to be a simple closed curve in a surface S if alpha, it is a map from circle to the surface S. Such that alpha is injective. And also you have to assume it is also continuous. So by a closed geodesic, we mean a simple closed curve such that, so if let us take this simple closed curve to be alpha. So by a closed geodesic, we mean a simple closed curve alpha if PQ belongs to alpha. So then again, so we'll alpha of S1, let us. So P of P and Q, it belongs to alpha S1. So means that, so then there exists theta 1, theta 2 belongs to your S1 such that alpha of theta 1 is equal to P, alpha of theta 2 is equal to Q, and so alpha restricted to, so one of this arc. Let me write in this way. So we have a map from this circle to the surface S. So this is my point P and this is my point Q. Sorry, so this is my point theta 1 and this is my point theta 2 and this is my map alpha. So alpha restricted to theta 1, theta 2 is a geodesic in S. That means either this portion is geodesic or, so alpha restricted to, let me write in this way, theta 2, theta 1 is a geodesic in S. So that means the other part, so this part, so alpha restricted to this thing, it is a geodesic in S. So that is the meaning of closed geodesic in the surface. So here we are taking this S to be the flat torus. So here is this flat torus. Okay, so now we want to find closed geodesics. First, let us give an example. If I take this point and this point and join them by a vertical line, so this will be a closed geodesic. In fact, if I take any other vertical line, so this is again, it is a closed geodesic. And now if I take any horizontal line, so this will be also a closed geodesic. So let me give you another example of a closed geodesic in the torus. So this is my flat torus. Now if I take this point, so this is, let us call this point to be my origin. So this point is half comma 0, this point is 1 comma 0, this 1 comma 1, this is half comma 1, and this is 0 comma 1. Now first take the straight line joining this origin and half comma 1. So this half comma 1 is identified with the point half comma 0, and you take the straight line joining half comma 0 to 1 1. So this two blue parallel lines, so this will form a closed geodesic is a closed geodesic in torus, flat torus. In fact, in flat torus, you can completely describe the closed geodesics. So how do you do that thing? So we have a covering map P from this R2 to, so this flat torus. So P is a covering map, and P is also a local isometry. Now if I take a straight line passing through origin and it will end at some point PQ, where this P and Q, they are again integer points. So then if you project down that path to the flat torus, so it will form a closed geodesic. So let me write down. So let alpha be a straight line joining origin and PQ, where this P and Q both are integers, in R2. So that is alpha t. It is nothing but 1 minus t of 0 0 plus t of PQ. Convex combination of these 2 points. So now, so what you can prove that, so exercise, so P of alpha is a closed geodesic in in the flat in the torus T2. So here I need to assume one more thing here. So this P and Q are co-prime to each other. So GCD PQ is equal to 1. So why I have to assume that thing? Suppose P and Q are same. Let us take P equal to 2 and Q equal to 2. Now if I take the straight line joining origin and 2, it will pass through the point 1, 1. If you project it down to the torus, it will wind the torus twice. So 0, 0 to 1, 1, it will you will get a simple cruise curve, and from 1, 1 to 2, 2, again you will get the same simple closed curve. So it will be winding twice. So therefore, that P of alpha, it will be not an injective map. So therefore, you have to assume this GCD of P and Q to be equal to 1. Okay. So another observation in torus, this is my torus, opposite sides are identified. So if I take two vertical closed geodesics, so these two are different vertical closed geodesics. So both of them are closed geodesics. So they are homotopic to each other. So these two geodesic, closed geodesics, so they are homotopic to each other. So if I take a closed geodesic in the torus, so in its homotopic class, so you can get hold of another geodesic. Now if I take hyperbolic surface, so there also you can get closed geodesic, but in the homotopic class of a closed geodesic, you'll get only that geodesic only. Okay, so let me state that thing. Okay, so let S be a hyperbolic surface. Let me write it as a proposition. Let S be let us take it to be a closed hyperbolic surface. And alpha be a simple closed curve in S. If alpha is not null homotopic, so then alpha is homotopic to a unique closed geodesic beta in S. I'll be not proving this proposition. So to get a proof of this thing, so refer to this book, A Primer on Mapping Class Group by Farb and Margalit. So I'll just give some examples of closed geodesics in hyperbolic surface and give an idea to prove this proposition. Let us recall, so how do I get a hyperbolic surface? So especially this genus 2 surface which admits a hyperbolic metric. So how we have done that thing? So we got a 8-8 tiling of this unit test model of this hyperbolic plane. So we have this regular octagon here, geodesic octagon in this hyperbolic plane, and we have the side pairings by isometries of this hyperbolic plane. So here in this geodesic octagon, the red geodesic is identified with red geodesic, geodesic is identified with green one, blue geodesic is identified with the blue geodesic, and the black geodesic is identified with the black geodesic. So now to get a closed curve or a geodesic in this hyperbolic surface. So first let us take this point. So this point will be identified to some point here. And that we can join them by a geodesic. So this 2 points here, this P and Q, so they'll be identified to a single point in this surface sigma 2. So in this hyperbolic plane, so this in fact it is a geodesic. Okay, now the question is, we project it down, so it will be a first of all a simple closed curve in this sigma 2, that surface. So it will be something like this. Now the question is whether this is a geodesic or not. So this may not be the case. So here, so this geodesic, blue geodesic, it is homotopic to this black geodesic. So this black geodesic. So this is also a geodesic in the ND2. And if I project it down, let us call it to be P prime Q prime. So if I project it down, so we'll get this black closed simple closed curve. So this blue simple closed curve is homotopic to this black simple closed curve. So that part is clear. So let me give a name. So this blue one, let us call it to be alpha and alpha tilde. And if I project it down, let us call it to be alpha. The black one is beta tilde, and the black one in the downstairs it is beta. So alpha closed curve is homotopic to the closed curve beta. Now by homotopy lifting property, so this alpha tilde beta tilde, so this will be also homotopic to each other. So in the other tiling also you can extend this alpha tilde. So you can extend this alpha tilde in the other direction. So you'll get a bi-infinite geodesic. And similarly, you can do it for this beta tilde. So alpha tilde, beta tilde, you can take it to be bi-infinite geodesics. And it, if you project it down, so you're getting two curves, alpha and beta. So this alpha and beta, it is homotopic to beta. So now if I take this region, lift it up, so you'll get this green region, and other tile also you'll get this green region. And it turns out that so alpha tilde and beta tilde, they lie in a uniformly bounded neighborhood of each other, and these two are alpha tilde and beta tilde, that they are bi-infinite geodesics. So in the boundary, that is the circle S1, so they will meet at a single points. So the endpoints of this alpha tilde and beta tilde, they will coincide. So alpha tilde infinity will be same as beta tilde infinity, and alpha tilde minus infinity will be same as beta tilde minus infinity. Now, so the endpoints, it will coincide, and this D2, it is a unique geodesic space. So this will be a unique geodesic space. So therefore, this alpha tilde and beta tilde, it should also coincide, but that is not the case. So therefore, so here, so this alpha tilde, so this length of, as per the picture here, so length of this part of this alpha tilde is greater than length of the part of this beta tilde. Okay, so now if I project it to the surface, so this alpha, it will be not a closed geodesic. Is not a closed geodesic. But this beta, so this will be a closed geodesic. So that is why, so in this proposition, so if I take any alpha to be a simple closed curve, which is not null homotopic, then it's in its homotopic class, so there exists a unique closed geodesic beta in S. Yeah, so here the picture of closed geodesics, it will be also very complicated. So I'll refer again to this book, A Primer on mapping plus groups by Farb and Margalit. For more details on closed geodesics in hyperbolic surface. Okay, I'll stop here.